Hi, this is our Cfd Final Presentation. My group consists of me, Kiera Edgepoint, Michael Barrera, and Cesar Gonzalez. Before we start off with what our problem statement was for the class, I would like to describe what CFD is. CFD stands for Computational Fluid Dynamics. It's a tool used for generating solutions for fluid flow with or without solid interaction. CFD uses math, physics, and a computational software to utilize how a gas or fluid flows. It's typically based on the Navier-Stokes equation. You can use it to solve for velocity, pressure, temperature, and density of a moving fluid. There are many applications in which you can use a CFD program to solve for what you need. Recently, with another project, we learned that you can use CFD in the food industry. Here are a couple other industries we listed. You can use it in aerospace, automotive, building HVAC, chemical or petrochemical, energy or power generation, manufacturing, or process engineering.
There are many reasons CFD is being widely used today. Firstly, CFD foresees performance before adapting or execution in systems. It can forecast the changes in the design layout to better improve the performance. CFD models precise and detailed information about heating, ventilation, and air conditioning design parameters. CFD modeling saves cost and turnaround time, and it produces reliable results. This is the reason CFD analysis reports are accounted as completely reliable. As mentioned, we're doing a CFD project. For our project, we are looking into a whistle and what causes a whistle to make noise. First, how a whistle works. First, when you blow into a whistle, of course it goes one side and comes out the other. It has no breakthrough at another part of the airstream to get out of the top. This creates an unstable situation with the airstreams fighting for dominance. They alternate thousands of times per second, creating high-pitched sound. The frequency of this sound depends on the length of the whistle. How we will be conducting our experiment is by a comparison of two different types of whistles, a referee whistle and a duck whistle. As you'll see on the following slides, the geometry of our model is depicted the inside of the whistle and not the whole thing. We'll see which whistle had the best airflow.
So to begin your simulation, first open up your ANSYS workbench and select the Fluent option under the Analysis System toolbox. Once you have selected the Fluent option, you will see a small box. This small box will guide you throughout the model simulation until you have obtained your results. The first thing that we're going to do is we're going to right-click on Geometry and select the Properties tab. Here you would change the analysis type from 3D to 2D under Advanced Geometry options. Once you have done that, you will right-click on Geometry once again and select New Design Modeler Geometry. Here you will begin to create your model. Once you have created your desired model geometry, you will exit your geometry modeler and start creating your mesh. The first thing to do here is create your inlet and outlet ports by naming them. You will right-click on the line and select Create Name Selection. Here you will name them either inlet or outlet, respectively. Once you have created your name selections, we will create your mesh using an all triangles method. To do so, we will go under the Mesh Control tab, select Method, and select Triangles under Method. Update your mesh, then once again, go to Mesh Control, then select Sizing. Sizing is done around the edges to better improve your mesh. Once you have created your sizing where needed, you will then need to refine your mesh. Once again, go to Mesh Control, select Refinement, and select either 2 or 3 under the Refinement Details. Once you have updated your mesh, exit your mesh window and begin setting up your solution under Setup. We will select Display Mesh after reading, Embedded Graphics window, Workbench Color Scheme, Double Precision, and Parallel Processing options. Then click OK. Under General Solution Setup, in your Setup window, you will be creating a transient simulation. Under Time, select Transient and Continue. Under the Model Solution Setup, we will change the viscous laminar to K epsilon. Everything will remain as default. Then we will move on to the materials. As a material, we will use air, of course, as we will be blowing into a whistle, and leave all the properties as default. Then click Close. Next, we will change our solution methods, but before you do so, make sure you change your boundary condition velocity under inlet velocity. In solution methods, we will change the momentum to second order upwind, turbulent kinetic energy second order upwind, turbulent dissipation rate second order upwind. Then we will move forward to solution initialization, where we will select hybrid initialization. And next, you will set up your solution animations. Go to Calculation Activities tab, select Solution Animations. Then, change iteration to time step. The storage type will be an HSL file. Then under Animation Object, create a new one. It will be named Contour 1. Select either the velocity or the pressure contour and select your desired properties. Once that is done, exit, and on the Animation Definition window, select Contour 1 and open. Then close the window. Next, you will run the calculation. The time step size will be 0.005, and the number of time steps for our particular geometry was 200. The max iterations will be 30. The reporting interval will be 1. And then click Calculate. Once your simulation has finished calculating, you will be ready to set up your animations. Go under Results, go to Animations, select Contour 1 or Animation 1. Change the file type. Select the file type MPEG and start writing the animation video. This will create your animation video under your ANSYS folder.
This is the geometry and the mesh of the first whistle choice that we chose, which was the referee whistle. From the mesh, you can see we did the all triangles method mesh. We chose a refinement of 3, and on the edge sizing, we did sizing on the inlet, which is the part you blow into, the outlet where the air is released and makes the sound, and the walls of the whistle. With all of the things that we learned in CFD, we were able to run a velocity and a pressure animation of the whistle that we chose. This is the animation for the velocity of the first whistle. You can see the air enters through the inlet and exits straight through the outlet at the top. Here we have a little bit of velocity that goes around part of the whistle. For the pressure, we can see that it fluctuates a little bit before it just goes back to normal. This is the geometry in the mesh of our second whistle choice, which is our duck whistle. Here you can see that the geometry is a little different than the referee whistle. We have one inlet and two outlets in a straight body. With the other whistle, we have one inlet, one outlet, and a circular body. To be fair, we did the same setup for all two whistles. We did a refinement of 3 with the all triangles method mesh, and we did an edge sizing on the inlet, outlet, and the walls of the whistle. We also did a pressure and a velocity animation for our second whistle. Here you can see that the pressure entering the whistle isn't as strong as the pressure entering the first whistle. It enters the whistle a little softer and it exits through both holes. We can see with the velocity animation that the velocity entering the whistle and the outlet is a little stronger, and then it fades off a little bit and releases through the first hole, and anything that didn't get released through the first hole releases through the second hole. This is which causes the variety of noise that you hear when you hear a duck whistle.
Here in the results slide, we see much of what Kara was mentioning in her presentation. However, if we look at these results in terms of sound, we see that in the referee whistle, it produces a single sound with almost no manipulation to the sound because there's only one outlet. However, when comparing it to the duck whistle, there are 2 outlets, so we can see how it would be easy to manipulate the sound by covering one or multiple holes to produce different frequencies and sound waves. If you'd like to see where we got our information and inspiration for this presentation, please look below in the details for links to where you could research what we researched. If you have any questions, please feel free to leave us a comment and we'll get back to you. Thank you for listening to our presentation.